Okay, so the the first thing I wanted to do was just in case. So I know we did a lot of this, but just in case people didn't actually get to see the triple point happen, I know most people did, which is good. But just in case, I wanted to kind of show you guys some videos so you could see what you should have seen. Um, so this is in the way, and that's annoying. Okay, hold on. I'm gonna have to start it first and then make it full screen. All right. So this is kind of what you should have seen. Um, well, it's not him. I don't.
Nice clear view. I'm gonna put on the bottom just to help me keep it steady.
I have the money shot. So.
Okay. So what you'll notice is it's solid, right? And then it starts to do what?
Melt.
Yeah, it starts to melt down, right? And then when there you go. And then when it gets covered with the liquid, it's going to start to boil. Okay. Now, I don't know. I don't know. I don't know
Does
why.
he have like stronger plastic or what?
Yeah, it could be.
Let's see.
Let's see.
Cover this up to keep it,
Let's see what he says.
ready for
Does his explode?
and now
Yeah, it should.
here's my little
Did you watch it?
rod and bar
No,
across there. The pliers.
he's got a little different. He's got something to help him clamp.
What goes on? You can see how the condensation is already starting to block the view of it. As soon as I put it in there, you get a nice clear view. I'm gonna put it on the bottom just to help me keep it steady. And right now the pressure is building up in there. And if it were leaking, I'd probably hear a little noise, but I'm not, so I'm pretty sure it's working. And there it goes. See it start to melt. At this point, we release the pressure a little bit.
Oh,
Do a solid piece of discord up there.
okay.
There's the triple point.
I have a really random
There's the drop into
question.
the solid gaseous
Hold on.
formation. So I can kind of fine tune where I'm on that phase diagram, moving up and down. I'm cracking off again now.
So he's increasing and decreasing the pressure by he's got that little bar thing and he's opening it. There's a slow motion of it. Okay. So yeah, what was your question?
Never mind. I'll wait.
No, go ahead.
It's like really random.
Is it about this?
No.
Okay, then hold on. So uh so that's kind of interesting. I've never tried it like that, but like he was actually with that little clamp thing he had, it was allowing him to release some of the pressure, and that's when you saw it like jump, like kind of like bounce back into a solid um, from there. So, but you could see how it melted and then it started to boil all together, right? Now, this one, you're going to see something similar, and that other one actually showed it pretty well too. But so he's got it in a. This is a like a more solid container.
You know, you can just click anywhere on the screen to pause it, right?
Okay. Yeah, but I need to be able to rewind it, and I can't grab it if it
Oh.
isn't there. Okay, so like it's doing the triple point thing. It's melting, boiling, or whatever, and then he's gonna release the pressure. And look what happens when he does that. When he releases it, you can see it turn back and pop back into a solid. And then he recloses or whatever, which we've seen. Yeah, it's just a really close up. It's crystallized. It's um, like more as like crystals instead of kind of like the shredded that we have, and like the stuff that when we do it too. Another thing is, so remember on the outside of the test tube or the pipette, how it got like frosty on the outside. Anybody remember what that was?
Water. Right?
Yeah, like water vapor from the air because it's so cold. that when water vapor from the air around it hits the pipette, it reduces the temperature in the air, and that causes water vapor to form right into a solid on the surface, on the outside surface. So that's actually water vapor on the outside. On dry ice, I know it sounds kind of weird, but on the dry ice itself, because the dry ice is so cold, you can actually get water vapor turning into ice, frost on the dry ice itself. So you can get water, frost. You can get frost forming on the dry ice, even as it sublimes and stuff. So that's what I mean, and that's another reason why ours look a lot more frosty and crystallized too. So okay. So again, like I said, I just wanted to show that. I mean, you guys, hopefully you guys saw that in real life when we were going through it. But in case you didn't, I wanted you to kind of give a view of that. So, all right, we are going to go through. Let's start here. Okay, so data table. All right. So you need at least 2 observations for each one, and then the phase changes observed, you need however many you observed for these, and then the other observations, if you saw phase changes, you should write them in. If you didn't, that's fine. So what were some of the, now remember, we've got observations about, like, so you're thinking about data, observations, stuff that you saw. It could be, felt, smelled, whatever, but mainly saw probably with this one. So when the bulb was submerged. Yeah. Okay.
I was gonna say the plastic tube kind of got larger.
Yeah, good. So you saw bubbles form. The plastic, the pipette expanded, right? So you saw bubbles form which means it also, you had a liquid as well, right, in there. So any of that works. I'm not writing on this because I need this for other ones. So.
Can we put the liquid in the small box?
No, put all that in here. And then the phase changes are the actual, so what are the actual names of the phase changes that we saw? Melting is one.
Boiling.
Okay, so generically,
Evaporation.
yep, vaporization. Yep, so yep, this stuff's going here under phase changes observed. So melting, vaporization, and then there was kind of one other one.
Sublimation.
Yeah, sublimation. So that's going directly from the solid to the gas as well. So sublimation, melting, vaporization for this here. Okay, now when the pressure was released, so and we saw it on those videos too, what happened, excuse me, what happened when the pipette blew or the pressure was released? What did you guys see happen? Okay, okay, so there's like a vapor, right? Like last time you had a vapor, and then I heard some other, what'd you say? Okay. Oh, okay, same thing. Okay, so vapor produced or
say the
released.
liquid all boiled off.
Say that again.
The liquid all boiled off.
So it actually did something weird. It didn't technically boil off. I think somebody else said it, but I know a lot of people said. What did you guys see like when they released the pressure on the video?
Went back to solid.
Yeah, actually it turned. So you saw like vapor released when it ruptured, right? And the CO2 turned back into a solid. Because if you remember, like right before that rupture, you got the whole triple point thing going. It's like a lot of like there's like liquid and bubbling and maybe a tiny bit of solid in there, but like it's mainly like that. And then all of a sudden, boop, if you look at it, it's like all solid again, whatever's left, right? So turn back into a solid. Good. So phase changes observed. So
Wait, would you write the general update?
so we had like vapor, like CO2 vapor is released, and CO2 CO2 turns back into a solid. Okay. And then so phase changes, freezing,
Deposition.
yeah, deposition could be one.
Vaporization.
Vaporization. I would say for this one I want at least you can have some of the other ones too, but I want freezing for sure because going back to a solid from that, and and then either vaporization or sublimation or both at least. Now you could have deposition too because that some of that could have happened a little bit, but for sure freezing and then like sublimation or vaporization because of the vapor that's being released. All right, other observations are just general stuff. One thing we talked about that you can put on there was that
Water freezing on the
Yeah.
deposition.
yep, water vapor turning to ice on outside of pipette. So water vapor to ice on pipette, if you want to shorten it to fit it. Water vapor to ice on pipette. What phase change would that be? Anybody know? You can actually put a phase change for that one.
Freezing.
Not freezing.
Deposition. Isn't it water
Yeah.
part? It's going
It's not, but they're not liquid, right?
Oh.
It's vapor, so it's deposition. Yeah, that would be deposition. So water vapor turning to ice, frost, or however you want to say it, on pipette would be deposition. So what were some other things just in general that anybody notice anything else? Did you have one?
I was just gonna say that it would freeze if it touched the water.
Oh, okay,
The water
okay.
would freeze if-
Sure. That'd be one. The water would freeze, and these guys, these are just generic stuff that you saw happen. Like, so water would freeze if the solid CO2 touched it.
Yeah, that kind of happened with mine. When you told me to
I think when it
change
flew
the
up-
grip, I set it down on
Uh-huh.
the table and I pinched it, and all around it there's just an ice.
Oh, okay. Yeah, like on the desk itself.
Mhm.
Okay. Oh man, I just had something in my head now. I can't. Oh, why do you guys think we put it in the water?
Because if you had it outside of the water, it would explode on us.
Okay, so that's one reason is the safety is the water absorbs some of that force, right? And I mean you saw we were hitting the ceiling with the water, so there's a decent amount of force there. So that's one reason. Okay.
It would increase the pressure even more because of like the pressure of being inside the pipette while being underwater.
Okay, so it's minimal, but yeah, being underwater does increase the pressure a little.
Oh, that's what I was gonna say.
Okay. There's something else kind of with that too. And it has to do with the temperature. Like, yeah.
But like when you put ice in water and then it melts eventually, it like kind of melts the.
Yeah, sort of. Yeah. Yep. Along those lines.
Because if water transmits heat a lot easier and like retains it.
Yeah, like water can has a capacity to absorb and transmit a lot of heat. Air is actually surprisingly, like a lot of people think air is not is a good conductor. Air is not a good conductor actually. So water is a better conductor of heat, so it can transmit. So it helps it happen more evenly and sort of and a little quicker as well. a little more quickly. Um, so putting it in the water, you could have something about like that, like helped it occur more quickly. Um, the I just had something with it. No, I can't think what I was going to say. Oh, similar to if your parents have ever, if your parents have tried to defrost something um, a little more quickly, but they don't want to put it in the microwave, and I put it in a bowl of water, right? And it helps, and that so that like one, it surrounds it, so it kind of evenly absorbs, absorbs heat evenly around the whole thing, as opposed to just one end or one side or something. Um, and it helps it happen more quickly than if you just left it out in the air. So, okay. And the phase changes observed, like I said, you can put one for some of the stuff that we saw, but like you didn't have to have multiple ones for that necessarily. Any questions on this? Okay, let's flip it. Post-lab questions. So this, now again, like that other part is kind of the data table. I just didn't have you guys fill it out while we were doing it because it ends up soaking everything and I'd have to reprint all the labs. So that was kind of like the data table. So these questions on number one actually just go pretty much with exactly what we just went over. So what was happening in the pipette at the following moments? When the solid CO2 was first enclosed in the pipette, you saw it start to melt, right? Solid CO2 started to melt. So go ahead and write that down for 1A. Solid CO2 started to melt. So B, when you got a decent amount of the liquid carbon dioxide, what did you see start to happen?
Saw a bubble.
Yeah, good. Bubbles started to bubble in the liquid. So, and here's the other thing. So technically, that was doing what? It's bubbling. It's vaporizing. Which vaporizing? Which part of it? Boiling or evaporation? Boiling. Yeah. So remember how I was talking about like you want to try not to think of the phase changes as like hot or cold. Like there's a good example. Like that's still really cold, but it's boiling because the boiling point of carbon dioxide is really low. So, okay. And then when the pressure in the pipette was released, when the pipette ruptured, you saw CO2 vapor released and turned back, and then the rest turned back into a solid, right? So some CO2 vapor released, rest turned back into a solid. Okay. Oh, I just thought of something. Okay, since I'm recording this, I'm going to actually have to do it on this paper here, I guess. All right. So let me grab some. Okay. So this diagram is a phase diagram for carbon dioxide. Okay. And all right, I'm going to leave. I'm going to leave this like the diagram up, so you guys can look at it as we go through the problem. So, let's start with label each area on the diagram with the appropriate phase: solid, liquid, and gas. So, where's our solid phase going to be? Yeah, this area in here, right? Yep. So somewhere kind of in here, you're going to go solid. Okay. Where is our liquid phase? Good. Liquid. And yes, you should be labeling these on yours. Okay, and then gas obviously has to be left over. Well, yeah, this area over here, right? So, okay, good. Then it says label the triple point. So where is our triple point?
-56 and 5.19.
Okay, good. So where all three lines meet, right? This. So this is our triple point. Oh, it's kind of all running together. That's right. Okay, triple point. All right. Now, I'll leave so in terms of like the labels, that's all we need to do. So number 4, okay, so if you guys want to turn, I'll leave this up so we can look at it while we do it. Number 4, when solid dry ice flex, liquid carbon dioxide and carbon dioxide vapor were visible in the pipette bulb, what were the temperature and pressure, and how do we know? So when solid dry ice, liquid carbon dioxide, and carbon dioxide vapor, when all solid, liquid, and gas were all visible in the pipette, what was the temperature and pressure with it?
-56.
Good. So what number is that, 14? Or 4, I mean?
4, yeah.
Okay. So negative 56,
Degrees Celsius.
56 degrees Celsius and,
5.11 atmospheres.
okay, 5.11 atmospheres. And we know how.
Because triple point is the only point where they can always exist.
Good. Because triple point is where all 3 states are present together. Good. So negative 56 degrees Celsius and 511 atmospheres, right? And that's because the triple points where all 3 states of matter are present together. Good. All right, number 5. Why did the carbon dioxide turn back into a solid when the bulb ruptured? Now this one's weird, a little bit. So
Because the air pressure was more intense.
yeah, so no, so like I said, it's kind of weird because so that we like the pressure is released, right? So you would think with like with the pressure release, it would like you think the pressure release, it would go to a gas, right? And we did see some vapor. So what happens is you get with that sudden release of pressure, yeah, the pressure drops. So you get some of it like you get some of it turning into a gas. Like we saw a vapor cloud, right? So you get some of it turning into a gas or into a vapor. But you also get, because then that energy, the energy that was being used to kind of hold them in all this, like at the triple point, some of that goes to as a gas. So some of the other, when it loses the energy, it actually turns into a solid. So it's kind of like some of it goes this way, some of it goes that way. So what we can say for 5 is because some of the CO2 turned into a gas, the rest lost. I guess lost is the best way to say it. I don't really like that, but I don't really know a better way to say it. Lost pressure, like pressure and energy. Well, we all lost pressure, but so lost energy, and therefore had to turn into a solid. Something like that. Because some of the CO2 turned into a gas, the rest lost energy or didn't have enough energy to stay a gas. So like basically you've got two choices, right? You could either like down if you lose pressure, if you lose pressure down to here, you basically got two choices. It can either a solid or a liquid. Or solid or a gas. So in order like some of it, some of that energy like gained and some of it went to the gas part and then some of it went to the solid portion. That's kind of the best way. It's not really a full explanation, but it's for what we saw, like it's good enough for what we're doing. Okay, everybody good on that? Number 6. Okay, human body temp is 37 degrees Celsius. Is there a pressure at which carbon dioxide could be a liquid at human body temp? How do you know? So if we look at this, human body temp is 37 degrees Celsius. So where is that?
It's off the charts.
Yeah, it's like way over here, right? So this is one that's actually kind of asking you to like look at the chart and like predict a pattern where if the chart kept going where stuff would be or whatever. So if we look like, so this is 6 right here. And this, by the way, this chart isn't to scale, which is kind of annoying in a little bit. But so 37 degrees is going to be somewhere over here, right? We don't know exactly where, but it's somewhere over here. Okay. So is there a pressure at which carbon dioxide could be a liquid inside the human body? What do you guys think? No? No?
Theoretically, yes. Like a sufficient temperature, like any gas could sort of behave like a liquid.
So, okay. So somebody first hour mentioned that too. Because, so you're thinking if like it gets past the supercritical point, right? So let's say that's not a liquid, because that's like a point where you can't tell if it's a liquid or a gas, so it's kind of its own. So like if we're talking about just get into this liquid area here, I would say generically, you guys are right that no. Like if you take this up, if we were to estimate a line up, and we were to look at the trend of how this line is going, it looks like it's very quickly, almost like exponential, like almost like a tangent line, right? Like looks like it's getting really straight there. It doesn't look like it's going to actually get over to this. So for number 6, I would go with you guys and saying no, because based on the graph, CO2 cannot be a liquid at 37 degrees Celsius. It just doesn't look like, we're predicting, but it's a pretty good prediction based on what the curve of that vaporization condensation line looks like, right?
How would that like affect us if it could be turned into a liquid, CO2?
So,
It'd be much like nitrogen.
yeah, I mean, you'd have like we're talking about like the bends and deep sea diving and stuff like that. Like it could affect you. But the other part of it is like what we have to realize is if it could, like we would also have to be able to withstand the pressure as human beings. Like we'd have to be able to withstand whatever pressure that would needed to be to get it to a liquid. So it depends. Like it depends on what it was. But yes, if it were a pressure that we could withstand, then we would have to um, we'd have to be careful of like it being basically like liquefied in our body wherever it is, like turning into a liquid or stuff. So those a lot of you guys didn't hear this. We had a discussion a few days ago a little bit about nitrogen's a gas in the air, right? And N2 nitrogen gas in the air. It's normally a gas. Deep sea divers, when they go really far underwater, the pressure of the water causes nitrogen in their bloodstream to essentially dissolve in the bloodstream, and it's like dissolve slash turn in kind of almost kind of turn into a liquid or be part of the bloodstream. And what happens is because it dissolves more of the nitrogen in the bloodstream, if they come up too fast, it's kind of like opening up a 2 liter bottle of pop. Like the carbonation in a 2 liter bottle of pop, you know how it comes out really quick the first time you release that pressure. Well, if divers come up too fast and the pressure of the water over them gets released too fast, then they can get a condition called the bends, which is essentially where nitrogen that was dissolved in their bloodstream all rushes out of the bloodstream at once, and they can get bubbles in their skin. And it can even if it's too much and too fast, it can kill them. So I can hold on. Let me pull up real quick. It's called it's decompression sickness is what it's called. But like you can see, I'll just show you guys real quick. You can see images of like what it can cause to happen. Trying to see, like they've got spots where it's like ruptured blood vessels because it comes out of the blood because it turns into a gas in the blood vessels too fast. So you can kind of see like type of symptoms. I'll get more pictures of actual like yeah, you can see like and in really severe cases it can you can actually even see like like bubbling on the skin. Usually if it's that bad it probably is going to kill them. That's a little different. So but yeah, you can see it causes like ruptures of the veins um, and blood vessels and stuff in the body because the nitrogen comes out too fast and it forms. So
Is that just with nitrogen, or is there other?
that would be with any gas that the pressure causes it to be dissolved in the bloodstream. If it's part of our body as a gas and then the pressure causes it to be dissolved, I mean that would be. And now nitrogen's one because there's such a large percentage of nitrogen in the air, then that's like a more of a concern because there's a large amount of it too. So okay. All right, number 7. In Challenger Deep, at the bottom of the Mariana Trench in the Pacific Ocean, the water pressure is 1,072 atmospheres. And the temperature can be as low as 1 degree Celsius. What state of matter would carbon dioxide most likely be in at this depth, and why? Okay, so the first thing, as I kind of mentioned previously, I understand why it's like this, but it is a little bit annoying. This diagram is not to scale. And what I mean by that, if you look, like the distance between here to here is 5.11 to 67. That's supposed to represent a distance of like 52 or 62. I mean, sorry, 62. Yeah, and then this is 5, and then this is like another 5, which is way bigger than, so it's not to scale, okay? So 1,072 atmospheres is way, yeah, is like super high up, okay? And the temperature is -1, so that would be somewhere probably like in here, okay? This one can be kind of tricky because like if you're thinking of like 1,072, like that's probably, you know, like if I do this, like it's probably like way up here. Because I mean, this is 72, so you've got another 1,000 to go, right? So if you look at this one can be a little tricky. What do you guys think?
Solid.
Liquid.
That solid, liquid. Why do you say solid?
Because the line keeps going.
Yeah. So most likely it'll be a solid. You can see this line here between the solid and the liquid.
Oh, it's angled.
Yeah, it's not really steeply angled, but it is angled a little bit, right? And if the pressure is like way up here, this line does keep drifting to the right. So probably by the time we get up to over 1,000 atmospheres, that line will have drifted above the -1. Okay, now that's based off the graph. Let's also talk just for a second about just the concept. 1,072 atmospheres is a crazy high pressure, right? Like super. That's like, have you guys ever heard of what's called crush depth for submarines? Like if they go down too far, the pressure literally will cause them to crush in like a can. So we know that the pressure gets really tremendously intense, like high, right? So if you've got a crazy high pressure, what do you think that's going to do to carbon dioxide molecules like that are down there? Yeah, because
It could be pushed together by pressure.
yeah, they're gonna be like, I mean, that pressure is just compressing them and jamming them together, right? So more than likely, so yeah, if we look on here, we could probably figure that out based on this, but we can also just think of it logically, like the idea that, man, all that pressure is gonna give those carbon dioxide molecules no other choice other than to be together. Okay, so for 7, just say the super high pressure will force the CO2 to be a solid. Something like super high pressure will force the CO2 to be solid. Okay? Everybody good? Now, here's what I want you to do. On your way out, make sure your name is on it